Hi folks, welcome back to Physics with Captain Rod. I'm making this just kind of a review video about Newton's theory of gravity. So first of all, let me talk about this first picture right here and move it off to the side. So here's a planetary side object, and Newton's theory of gravity basically is this, that what causes the gravitational force is a quantity called the gravitational field. And if I were to pick a spot like right here, the gravitational field is a vector that points towards the center of the planet. And it is defined as force per unit mass. Now, as an example of that, what does that mean? Well, it means, like, let's say I put an object here, right here. And that object, I measured this force on it, and it's 20 newtons. And then I measured the mass, and it's 10 kilograms. Then the gravitational field strength at this point would be 20 newtons over 10 kilograms, or 2 newtons per kilogram. Okay. Here at the surface of the Earth, if you did that exact experiment right there, the gravitational field strength anywhere on the surface of the Earth is approximately 9.8 newtons per kilogram. Now, as you get further and further and further out, you'll find that the gravitational field strength falls off. Now, so that's part one of Newton's theory of gravity. Here's how the gravitational field is defined. Part two. Here's how this thing is calculated. The gravitational field is directly proportional, means some constant times the mass creating it falls off with r squared. This proportionality constant, that's called the universal gravitational constant, the UGC here, and I'm not going to bother with its numerical value. I've written it down in other videos. Okay, this is, honestly, a really simple equation. It just says that the gravitational field created by mass is proportional to how much mass falls off with distance, and that distance would be from the center of the planet or object to whatever this point is. Okay. 3. If you put 1 and 2 together, you get that the gravitational force between any two objects is g times the mass of the first object, mass of the second, over r squared. I usually put like big M and little m because in a lot of problems one of these things is planetary size and one of them isn't. But you can put M1, M2, or mass A and mass B, it doesn't matter. But that's an M right there, by the way. There. And then third, as a consequence of this, and I'm going to skip the mathematics, but I'll do a quick overview. When you plot the gravitational force, like imagine we have an object here, and then we remove it. We take it infinitely far away. And when you plot force against distance, this function has this type of behavior to it. It has a vertical asymptote at r equals 0, so this would like go straight up. And then it has, when r goes to infinity, this whole thing goes to 0. So it has this kind of general shape. This area right here is equal to the work done to remove that object. And in magnitude, it's equal to g big M little m over r. Now, what that means is that the potential energy of an object at this location, and it's really the object and the Earth together as one system, is minus g big M little m over r. I'll make another video here, I think, about why the potential energy term actually is negative. But anyway, that's kind of Newton's theory of gravity in a nutshell. It starts with this. This is what the gravitational field, or how it's defined. 2, this is how the gravitational field is calculated. 3, a consequence of 1 and 2. When you put these two things together, you get this, how the force between two objects is calculated. Let's see, 1, 2, 3, I guess this should have been 4. 4, therefore, gravitational potential energy is equal to this expression, and that comes from the area under this curve, and I'll make other videos about that. That's not meant to be, this is just meant to be a quick overview. Now, another big thing here in a standard like college physics class, what would we expect, to do with these things? Well, here's a couple of examples. I'm going to call this like case 1 here. Objects in orbit. You would use Newton's theory of gravity, particularly this part of it, to calculate the force on some sort of object. Where in this example, this mass would be the mass of the Earth, or whatever planet this happens to be. and then this mass will be the mass of this satellite or whatever it happens to be. This could be another planet as well, or it could be a piece of space rock or something. And by Newton's second law, this object is accelerating inward. So this is equal to mv squared over r. So this is typically one piece of math that's used for analyzing orbital type problems. Another very common one that goes with it is speed is distance over time. Speed is the magnitude of your velocity, that's this v here, and for one revolution the distance is 2 pi r. And then this time is specifically the time for one complete revolution. Right, another common case where we'd be using stuff like this, all right, I'm going to call this case 2. Here's an object that's within gravity's reach, and in this case, we're going to imagine it's kind of moving away or towards, but the big thing is not in orbit. Right? It's moving in such a way that it's moving towards, in this case, higher potential energy. So here we would use the work-energy theorem probably on a problem like this. The PE1 plus the KE1 plus work equals PE2 plus KE2. And where Newton's theory of gravity will show up is this term will go under the potential energy terms here and here. So that's two very common cases that you would be perhaps asked to use Newton's theory of gravity. And then I'll just put for, let's see, I need some space here. I'm going to put an other case here, okay? Let me just kind of move this stuff. I need a little more room. Scale it down, move it over. Case 3, again, I'm just going to call other things. I don't know, you could calculate the gravitational force of attraction between any two objects here, between two people. Or maybe you're looking at some other type of planet here. I like to use Vulcan in a lot of my examples. Where are my planets here? Planets and moons. Oh, we'll say there. Vulcan's kind of a dry, dead world. We'll use this. All right, so planets about maybe the gravitational field strength, or sorry, problems about the gravitational field strength at the surface of other planets like our moon or Vulcan or Kronos or any other planet you can think of. And then once you knew, like what the gravitational field strength is at the surface of these unknown planets, then you could do all the other things that you've done in physics, like you could define potential energies for that, MGH terms, and you could apply the work-energy theorem. And you could do all the kinematic stuff that you've done maybe in a physics class here on the world. You could do all that same stuff on the other planets, so to speak, using Newton's theory of gravity to predict the gravitational field strength at the surface of the planet. So, case 3 here is really kind of unlimited. I mean, there's all sorts of types of problems I could make up having to do with calculating gravitational fields. So anyway, just meant to be kind of an overview of Newton's theory of gravity, and the big equations and kind of what they might be used for. I hope that this has helped you out. Have a great day.